Hey, what up, girl? How you doing? I don't want to come on.
Imagine you are riding a bicycle down a steep hill. You squeeze the brake lever, and the internal cable snaps under the tension. The result is a total loss of control and a severe crash. To stop that from happening, engineering teams look for structural flaws months before manufacturing begins, while the bicycle is still just a digital blueprint. The global standard for finding these flaws is the AIAG VDA FMEA. It is a structured risk assessment methodology used across the automotive and manufacturing industries to identify potential failures, determine their causes, and implement actions to reduce risk. The methodology is broken down into 7 distinct steps. We are going to apply every single one of them to our baseline example, the mechanical front braking system of a bicycle. By working systematically through this sequence, engineers can accurately predict where a design is vulnerable and correct it before a physical prototype is even built. Step 1 is planning and preparation. This is where we define the exact scope and boundaries of the analysis. For this exercise, we are isolating our focus strictly on the front braking system, excluding the rest of the bicycle. Step 2 is structure analysis. This diagram breaks our targeted product down into a clear hierarchy. We map out the relationship from the highest system to the subsystem down to the individual component, which in this case is the brake cable. Moving to step 3, function analysis, we define the exact mechanical job expected of each element in that hierarchy tree. For the brake cable, the assigned function is to transfer tension from the lever to the caliper. Establishing this specific job is a mandatory baseline requirement. You cannot determine how a part fails until you identify what it must do. Step 4 is failure analysis. To find a failure mode, simply define the exact opposite or absence of the function we just established. The ability to transfer tension shatters, leaving us with our failure mode. The cable snaps under tension. This spreadsheet maps out a logical risk chain. We record the failure mode of the snapping cable. We track its effect, which is a crash. Finally, we establish a root cause, such as the selected steel material being too thin. Step 5 is risk analysis. We evaluate this risk across 3 specific criteria: the severity of the effect, the occurrence of the cause, and the effectiveness of our detection methods. This matrix table introduces the action priority framework. Older legacy systems relied on a risk priority number that simply multiplied scores together. The AIAG VDA methodology uses this strict logic matrix instead to determine which risks require immediate attention. Looking at this matrix, assume a severe crash carries a high severity score of 9, and a material defect has a moderate occurrence score of 4. Pause the video and determine how a detection score of 2 versus a score of 8 affects the final priority. Under the AIAG VDA matrix, high severity and moderate occurrence immediately trigger a high priority flag, regardless of how good the detection score is. This forces engineering organizations to address severe safety risks immediately, preventing them from being mathematically hidden by older multiplication formulas. Step 6 is optimization. To resolve that high-priority risk, the engineering team implements actionable design changes. They can upgrade the cable thickness to eliminate the root cause entirely, or add a tension sensor to improve detection during testing. When we apply these design changes to the assessment, the resulting risk level drops down to a safe threshold. Finally, step 7 is results documentation. The team documents all decisions, assigned responsibilities, and outcomes to support future learning and continuous improvement. This final chart shows the complete 7-step process mapped directly to the documented output for the bicycle brake. You can use this standardized flow to structure your own engineering risk assessments. The AIAG VDA FMEA is a systematic approach to building quality, reliability, and safety into product design from the very beginning, because the best failure is the one that never occurs.
Hey, what up, girl? How you doing? I don't want to come on too strong or nothing like that, but